Hello. Okay, so physics 1112, second semester, algebra based, chapter 16, section 8, resonance and forced oscillations. So one of the best ways to look at this is, and I'm pretty sure everybody's seen a piano that's been opened up, and on the inside you have longer frequencies on the left. So longer frequencies, and then gradually the strings get shorter and shorter and shorter until on the right side you have very short strings. And so you play your lower notes on the left side and the higher notes on the right side. Well, a piano, let's get our piano here. A piano has 88 keys. And they all have different frequency. And it makes sense that the strings would be different for each of those frequencies, like we laid out here. So if you were to sit here in front of this piano, you sit right there and you sing a high note, or it doesn't matter. Sing anything, a note, loudly. Hopefully it'll be on one of the keys. It has to be, actually. So you sing a note loudly for, I don't know, a second or two. And whichever note that you happen to sing, let's say it's this, whatever the note is that string, the vibrations from your vocal cords will drive the string oscillations for the string with the same frequency. Only one of the strings will vibrate. So it's the string with the natural frequency So natural frequency is the frequency that an object or system resonates at. So let's go back up to our strings. So each of these strings at the top resonate at a certain frequency. The one that we selected from vocally when we sang in front of the piano, this one has a certain frequency. Who knows what that one is, but whatever it is, that's the natural frequency for that particular string. So it's just a number. Okay? And it has a length, and the frequency, of course, is due to the length of the string. We'll talk about that in a little bit, but we've already kind of seen that with pendulums, different pendulum lengths, and hopefully your experiment that you saw will show that. So the natural frequency is the frequency that an object or a system resonates at. And I should put a comma here if there are no driving forces or driving oscillations. So no driving forces or dampening forces. Damping forces. Resonance. Resonance is the phenomenon of driving an object or system at its natural frequency. So that's resonance. So let's put it a different way. If we input with frequency of the object, the natural frequency of the object, then the object will resonate. it is in resonance. Let's just say it will resonate. So a system driven at its natural frequency is said to resonate. Okay, how do we find what that natural frequency is? How do we find that? What is that natural frequency? How do we find the object's natural frequency? Okay, great question. I'm sure one of you asked that question because it's so good. It's such a good question. What do I got to do to erase that? Okay. All right, so we have already done it. Yay, we've already done it. How did we do it? Well, first we had a mass on a spring. And we went through all of the algebra and analysis and all of that stuff, and we found the frequency for a spring is 1 over 2 pi k over m square root. So once you know k and the mass, then you have your natural frequency. This is the natural frequency. Okay? And we did the same thing for a pendulum. And we found that the frequency for a pendulum, the natural frequency for a pendulum is 1 over 2 pi times the square root of g over L. Okay, so that's the natural frequency for a pendulum. So pretty much everything has a natural frequency, and when something has a certain length, that tends to be a part of its natural frequency, right? We found that L was part of the pendulum's natural frequency. Well, the same thing goes for the vibrations on the string that we saw earlier up here. The length is what determines our frequency, and we're going to see that here in a second. Okay, so we have, I'll just leave these two equations there for a minute. I want to talk about springs and we know that the position for a spring, it goes as x max times the cosine of omega t, and omega is just nothing but 2 pi times the frequency. So great, that's true. And if we were to pluck the string, then we would be plucking the string. It has a length from here to here. We pluck the string, so we kind of put some tension on it, and we pluck it and let go. And this distance right here, that is our x max. Okay, great. And then it'll vibrate with that x max until the friction of the system stops it. But that's our x max. We pluck the string. if we drive that system, well, let's talk about the energy. So the energy, potential energy, is going to be 1/2 k x max squared. But if we drive this string with an outside voice or something that is providing a sound wave that is at the same resonant frequency, then we will drive that system and it will accept the energy. It takes in that energy and it will grow. So X max will get bigger. So if X max is getting bigger, then the total energy of the string, which used to be at 1/2 k x max squared, will go up. So the total energy goes up as the amplitude goes up. So when we're driving that string's oscillations, we're driving at the right frequency. It will increase the amount of energy in the system or the object. This is our system. That also means that, of course, our kinetic energy will be going up as well, because the velocity will increase as it comes back and forth through the x equals 0. And this leads to consequences, actually, that we're going to talk about right now. So we have a system that we're driving, and we're driving it with sound. So the sound is coming in, the sound is coming in like this and driving that string, okay? Well, what if your string is a bridge? We're going to look at the bridge from, we're looking across the bridge from one side of the bridge to the other. So all we can see is just a flat bridge like this, and it has a width of L, and what I'm talking about right now is figure 16.28 in your book. Figure 16.28 shows in 1940 the Tacoma Narrows bridge failure. Crosswinds went across the wind velocity. The wind went across this bridge, and of course it's going above and it's going below and all of that. But the wind happened to be at just the right speeds that day to cause this bridge to start to do this kind of thing. So it started to vibrate, and it wanted to oscillate, and eventually it started oscillating like this, and then it got bigger and bigger oscillations till finally ropes and cables and all that stuff snapped, and we had a bridge that ended up in a falling situation. where pieces and chunks of the bridge, because it's concrete and steel and all that, it's not super flexible, it's brittle. And the bridge ended up falling into the water because the winds were coming across and the wind input more energy than the bridge was designed for. So what happens? This is the same thing with shocks on a car. You want to install shocks. You want to install dampeners. You want to install things that buffet the wind. They could have had some kind of a shield on one side and the other. There's all kinds of ways you can make the length or the width of the bridge. You could make that length or width smaller or wider. That helps with stability. A really long bridge, if it had double the length, the winds that day wouldn't have torn it apart. And the required winds would have needed to be far more velocity. The velocity of the wind would need to be much greater for a bridge 2 times as wide. Okay, much greater. So there's, you can go online and look at videos, find a video of the Tacoma Narrows. Tacoma Narrows Bridge. And you'll see it fall apart. It's quite dramatic. You wouldn't have wanted to be on that bridge that day, that's for sure. Okay, so the next thing that we're going to talk about, and this kind of leads up to it, is waves. So this is section 16.9. So let's draw a wave. And a wave is coming in, and a wave is really just a wave packet. And it has internal not too shabby. There's X. All right, so here is our wave packet. And it's just a displacement that we can visually see as it travels along a string or whatever, with a velocity, a wave velocity, V wave. Okay, that's our wave velocity. And the maximum would be here, amplitude, and that maximum amplitude is traveling at that wave velocity. Okay, along the string. So that's a wave packet. I consider these bodies or a disturbance, but the disturbance is also a body. So it's a wave packet, body, or disturbance. I forget I can just erase like this. That's so nice. So wave packet. All right. A uniform set of waves comes in. So here we have our wave situation. This is a uniform set of waves. There's a wavelength, lambda, and of course this isn't t anymore. This is the x direction. And lambda is what we call the wavelength. And this is our y direction. Plus y, minus y, and 0. Okay, and what else? So this is minus y max. This is plus y max. And this distance from there to there, of course, is 2y max. Very nice. So let's talk about this. One of the things that we always want to know is what are the wavelengths and the frequencies, the angular frequencies, the period, all that stuff. So here's how you can find out, and you can do this every single time. If you're on a test or whatever and you don't have equations, or it doesn't matter, you can just say distance x equals velocity times time. Okay? Now, all you have to do then, if these waves are traveling at velocity wave, then your distance that it travels, lambda, say from this point to this point, lambda equals your v of your wave times tau. Tau is the period of the wave, and I'm supposed to call it t, not tau. When you get into physics further and further, everybody calls it tau. Sorry. So t is equal to the period in seconds. Okay, so just knowing this equation gives us this equation. And then knowing that t is equal to 1 over f, and f, I like to write it like this, 2 pi f equals omega. Then we have all the other equations that we need. So we can write lambda equals vw, the velocity of the wave, times 1 over the frequency. You can find out what the velocity of the wave is by lambda f, which also equals lambda over the period. And then omega, of course, lambda times 2 pi omega. And you can then solve for omega as well. So omega equals velocity of the wave over lambda times 2 pi. Or 2 pi lambda, which is how most people write it. So let me write it again. V wave is 2 pi lambda. Okay, so every single equation that you would want is there. I did a mistake. I made a mistake. It doesn't look right to me. This is all bull. This means that omega equals, omega over 2 pi equals the frequency. So here I'm inserting the frequency. I have to do omega over 2 pi. And that makes more sense. So we can write omega is 2 pi wave velocity divided by lambda. So that equation, this equation, and these equations are important. Those are key. And of course, they all stem from these equations over here, which are more fundamental. So you can go from x equals vt and get a lot of stuff. Okay, great. Sorry about that. Get a little mistake in there. Let's do an example. We'll leave these up here, and our example will have waves that are coming in and it's waves in the ocean. They have a velocity of wave like so. Here's a crest, and the distance between those two crests is lambda. Let's say we put a beach ball here. So there's a beach ball in the ocean, and it's bobbing up and down, and I don't remember which way it goes, but it bobs like this. But essentially, it goes from this point down here at the trough to the crest. And the ball takes 5 seconds. 5 seconds to go from the crest to trough, OUGH, and back again. That means, what does that mean? Ask yourself. The period then has to be 5 seconds. Okay? Because it takes 5 seconds for it to go down all the way to the bottom and then come right back up to the top. So that's the period. And we know that, I guess we're given, I'm sorry, we're not given that. We're given that the crests are 10 meters apart. So lambda equals 10 meters. Okay. The question is, what is the wave velocity? What is that wave velocity? Good question. So I'm going to back down a little bit here. And the wave velocity, we're gonna want to use, oh boy. We're going to want to use this equation right here. And this part of it, okay? Because we know lambda and we know t. So that'll give us our wave velocity. So let's go back down here. VW equals lambda over t. And like I said, if you're not sure, you can just write out x equals vt. And v equals x over t, which equals our distance, which is lambda, over our time, which is the period. So we now have v for a wave, and that is 10.0 meters divided by 5.0 seconds, and that is going to equal 2.0 meters per second. So VW equals 2.0 meters per second. Okay. Great work, everyone. So, what types of waves can we have? There's the string gets plucked wave. So you're plucking right here the string, and then you let it go, and then it sets up its vibrations accordingly, which have an amplitude here. The wave velocity would be in this direction, and our amplitude is perpendicular to it. So when it's perpendicular, then that is called a transverse wave. So that's this situation. A longitudinal wave also called a compression wave is best thought of as sound, or a good example of it is sound. So how does sound work? Well, we draw a sound like this as it's propagating, so it has its VW going in this direction. The displacement, I'm going to see if I can draw, so here this is where the sound is emanating. Here's where the sound is being collected in the receiver. So here's our receiver. This is our speaker. And in between, we have sections where it's more condensed and less condensed. More condensed and less condensed. So it gradually gets more and more and more, and then gradually gets weaker and weaker, and then gradually gets more and more. So this would be the peak of the wave, but it's the peak of the pressure. And let's make it even more highlighted here. Okay, so this is more dense, okay? And they are going in this direction. So the density increases at different points, but it's not transverse. The compression happens in the same direction. So that's why we call it longitudinal. So it's parallel to the displacement. Here's our displacement. So that's a longitudinal wave. Sound. Sound is a longitudinal compression wave. So when we have a piano and we pluck the string on the piano, or we hit the string with a mallet or whatever, the strings do their thing, but when they do, they're compressing the air as they do. And so this string develops or generates a wave through air that is a compression wave through the air. So it has rarefaction in between. Here's rarefaction right here. I don't like using the word, but there's compression, and the opposite of compression is rarefaction. So this section is rarefied. Boy, I hope I got that right. Rarefaction. I'm not sure if that's right or not, but anyway, so this is the compression part and then the rarefaction part. So that's what happens, and that's why we draw it like this, as it comes away from the string, and then it goes in to hit your ear. So let's talk about that. Let's talk about your ear. More specifically, we're going to talk about your cochlea. And here's where I hopefully will draw. Oh boy. I gave up on that quick. Have you guys heard of the golden ratio? Well, your cochlea works with the golden ratio. On the very inside, you have little tiny hairs, but the hairs gradually get bigger and bigger as they can because of the shape of the cochlea. So when sound comes in, it resonates with, I don't like that I don't like this sound coming in. Let's do it more like this. So we have our sound coming in. The sound is going to resonate with a hair that happens to be this wide. And I'm not doing this justice. Hold on. Let's start it over again. The sound comes in. This is the wavelength. That wavelength is the size that the hair has to be to naturally work with it. So that sound comes all the way in. These hairs in this section don't resonate with it. The length is this long. So when it finally gets to this hair here, it tickles it, and there's a hair follicle with nerves. This vibrates, right? It does its thing. It does its little wiggly thing and starts vibrating. Triggers the nerves, which then send signals to your brain. And then your brain does all the processing, right? It does all kinds of stuff so that you can, when sounds come into your ear, you can make that work. And your brain infers all kinds of things like direction, the volume of the noise, the frequency or pitch. So your brain gets all kinds of stuff just from this cochlear ear, evolutionarily ear, whatever thing we've developed over all the years. Mice have them, we have them. It works great, and that's why it's designed like this. So different sounds will trigger different parts of your cochlea. Okay, we're going to stop there, and we're at the point of 1610 now, which is superposition and interference. Don't get lazy on me now. And interference. Okay. All right. Thanks for watching.